Good morning, everyone. So, looking at, we got plenty of participation up there on the whiteboard. Like seeing that. So, yeah, if you don't know already, the way to solving this problem is by just rounding the average atomic mass of aluminum to the closest whole number, which in this case would be 27. So then our correct answer would be aluminum 27. All right, we learned how to do that right before spring break. All right. Just as some disclaimers, please do not share any personal information during class. Your participation is vital, and we will call on you multiple times during the live session. And just keep in mind that these Class Connect sessions are recorded for educational purposes. All right, we are speeding through here. We are on week 4 of 13. We only get a 4-day school week this week, so yay for us. And then Thursday, as usual, will be a recording day where you will have time to work on the unit project. All right. And then for units and lessons, we're almost about halfway through. So we're going to start off by talking about the properties of nonmetals on the periodic table. And specifically talking about that, we will explain how atoms gain or lose electrons to create full valence shells. And then going specifically about metals, we will talk about how metals will determine if they love to gain or lose electrons. And then we will, using that, identify the characteristics of metals as we go throughout the lesson. And hopefully by then we will be able to show mastery of this by getting a 80% or higher on our course.
All right, everyone, let's go ahead and get our notes open and ready to go. Links are in the chat. Please raise your hands once you have it open and ready to go. Again, one link will work, the other one won't, so make sure to try both. Otherwise, you can just get to it directly from your grades tab as always. I'll go ahead and give you 30 seconds to get that open and ready to go and answer question number 1, saying you understand our attendance policy. Again, you can do notes at any time for your normal notes credit, but if you specifically do it during class, you get both your notes credit as well as your attendance credit if you do it during class and pass. Go ahead and raise your hands. Let's go, let's go. What I want to know in the chat, I want to know how many valence or outermost electrons does magnesium have? So take a look at our Bohr model of magnesium. Again, when we talk about the word valence, we're just talking about the outermost shell. So how many electrons do you see on the outermost shell? The color of the electrons does not matter. That has nothing to do with that. Go ahead and get your answers up in the chat. Thank you, Tara. Thank you, Rosa, Colleen, Creek. Excellent, Kaylee. Alejandra, Shane, perfect. Yeah, absolutely. If you take a look here, ignoring everything in the center, we're just looking at the outermost shell right here. So we can see 1 valence electron, 2 valence electrons. So it has 2 valence electrons. Taking a look at our chart, then therefore, what group must magnesium be in? What group must magnesium be in? Give me the group number. 1, 2, 13, 14, 15, 16, 17, or 18. What group number is it in? Thank you, Colleen. Thank you, Paul, Jaden, Umeza, Sophia, Rosa, Matt. Yeah, it's actually also in group 2. Remember that the group number is actually related to the number of valence electrons. If you take a look at the last digit of the group number, which group 2 only has a single digit, so it's group 2, has 2 valence electrons. Group 13, its last digit is a 3. It has 3 valence electrons. 14 has 4. 17 has 7, etc., etc. So it is in group 2, and we're going to be learning about the names of these different groups or families in a few lessons. So let's start to familiarize ourselves with those, taking a look at the chart. What is the name of group 2? What is the name then of group 2? The name. Take a look at the name column. What is the name of group 2? Yeah, no worries. Awesome. Yeah, this is going to be the alkaline earth metals. Again, you shouldn't have that memorized already unless you've learned it before. This is just familiarizing yourself with some of these vocab words. We'll be talking about all these different groups in a later lesson. So yes, these are the alkaline earth metals. This is different from the alkali metals. I know they have similar sounding names, but alkali metals have 1 valence electron. Alkaline earth metals have 2. Now, remember, based on the octet rule, how many valence electrons do most atoms actually want? All right, so think about that prefix oct, like octagon. How many sides does an octagon have? Or an octopus, how many legs does an octopus have? Octet rule means that most atoms want how many? Yeah, it means that they actually mostly want 8 valence electrons. So taking a look at our example here, magnesium currently has 2 and it wants 8. So if it has 2 and wants 8, is it happy? Is it stable? Yes or no? If it has 2 but wants 8, is it happy? Is it stable? Yes or no? It's sad. Exactly, it's sad. So no, it's not happy, therefore it's not stable. Smiley faces emojis in the chat if that's beginning to make sense. So magnesium is going to have to do something with these electrons, with these valence electrons, to try to make it more stable, more happy. We'll be talking about how it can change those electrons to become more stable and happy. Excellent. All right, this is going to be the answer to number 2. So magnesium has 2 valence electrons, and that group, therefore, is the alkaline earth metals group. So you should have 2 answers for number 2, 2 for 2. So go ahead and raise your hands for number 2. You have 20 seconds. Go, go, go. I already see like 10 of you with your hands up. Great job. On. All right, so let's go ahead and take a look at 2 different atoms here. So we're going to take a look at calcium. All right, Ca stands for calcium. And just taking a look at calcium really quickly, again, tell me how many valence electrons do you see for calcium? Again, valence meaning outermost. How many valence or outermost electrons do you see for calcium? Perfect. I see Shane, Tara. Awesome. There we go. Thank you, Sophia. Yeah, so if we ignore everything in the center, right, we can see that it has 1, 2 valence electrons. Now, again, this means that calcium's not happy. It wants 8 outer electrons. So there are a couple ways that you can get to 8 outer electrons. You can either gain electrons to fill up the current valence shell, or you can lose electrons to drop down to a shell that is already full. Okay, so let's go ahead and take a look here. This calcium has 2 valence electrons, so we need to think about if it had to gain electrons to get to a total of 8, right? The filled shell would need an octet, a total of 8. That would mean that it would need to gain 6 more, right? So you could gain 6 more, or you could just lose the 2 that you have. So tell me in the chat, what do you think is going to be easier? Just purely by numbers, is it going to be easier to gain 6 more or lose the 2 that it has? Easier to gain 6 more to get to a total of 8 or lose the 2 that it has? Thank you. I see Tara in the chat. I see Rosa, Matt, Sophia. Yeah, just by numbers, it's going to be easier for calcium just to lose the 2 that it has. So take a look here. If we were to lose the 2 right here, right? So if we just take away these 2 right here, then we can see that it drops down to a shell that's already full. And this shell has how many valence electrons? Go ahead and count them up. The shell underneath has how many valence electrons? Yeah, this one has 8. So this one is now a full octet, right? So this one is a full octet, has all 8. And so now calcium is happy. Happy, happy, happy. Smiley faces emoji since that makes sense. So when calcium bonds with other atoms, it wants to get rid of 2 of its electrons. That's the way that it bonds, by getting rid of 2 electrons so that it becomes happier and more stable. Excellent. Now let's go ahead and try selenium. So take a look at selenium. How many valence electrons does selenium have? Think about, what does the word valence mean? Count them up. How many valence electrons does selenium have? Yes, this one has 6, right? So we can see 1, 2, 3, 4, 5, and 6. All right, so this time it could either gain 2 more to get to a total of 8 or lose 6, right? So gain 2 more or lose 6. Go ahead and tell me in the chat this time, just by numbers, which one's going to be easier. For it to gain 2 more to fill up that octet and get to 8, or to lose 6 of them and drop down to a shell that's already full. Yeah, it's going to be easier just to gain 2. Just by pure numbers, it's easier just to gain 2. And so this type of atom will want to gain 2 electrons in order to become more stable. So let's go ahead and take a look at an example here, because these 2 can actually work together. Right? So if we take a look here, if calcium actually takes its 2 electrons and sends them over to selenium, this is a process called bonding, which we'll be learning more about in the next unit. But what you can now see here is now calcium has a full octet underneath, and selenium has the extra 2 electrons that it needs for a total of 8. So now calcium and selenium are both happy. They've bonded together. They both have this correct amount of valence electrons that they want. Go ahead, give me a smiley face or an emoji in the chat box if that's beginning to make sense. If you only have a few electrons, you prefer to lose them. If you have most of your valence electrons, you prefer just to gain a few more. And they can work together to make this happen. They can work together as bonding to make this happen. Great job, everyone. All right, let's go ahead and talk about what these are therefore called on the periodic table.
All right, so looking at the periodic table, what we have is actually 3 different types or categories for our elements. So first, if we're looking at the periodic table here, we have in our blue, most of the periodic table is classified as metals. Those are the elements that love to lose their electrons, as we just found out from our last slide. Then we have the nonmetals, which are in yellow. Those are kind of like the opposite of metals, hence their name. But yeah, when they have electrons, they tend to want to gain more to complete their valence shell. And then lastly, we'll go into more depth about this later on in our unit. But then we have the metalloids, which are kind of a hybrid between nonmetals and metals. Some tend to act more like a metal, whereas others tend to act more like a nonmetal, depending on the situation. All right, so for the octet rule, keep in mind that for most atoms, keyword being most, the full valence has 8 electrons. All right, but as we can see here with this group of elements, remember helium only has 2 electrons in its natural state. So, but even though it's perfectly fine with 2, it's still okay with those 2 electrons. But every other atom up from that starting point in that column, going from neon to argon and so on, they all have from that point a full octet of 8 electrons on the outer shell. All right. So let's move on from there. And moving forward from that, remember, we have a couple of properties about metals that we need to discuss. So firstly, right, if a metal has 1 to 3 valence electrons, then it can go down to a full shell by giving those few away, just like we did in the examples a couple slides before. All right, but this gives the metals the ability to have certain properties. A couple of them are known as being malleable and ductile. Being malleable means that you can be hammered into a thin sheet. So it's kind of like a very hard material, but once you hammer it into a shape, it holds that shape under normal conditions, kind of like this copper bowl that we see at the bottom. All right. With ductile means that you can be bent and stretched into a wire and not break. So such as the copper wire that we see right next to that copper bowl, we can see we have 2 separate uses for copper, but they both display these parts. Let's go ahead and give me a smiley face or a sad face or a medium face, depending on how you feel about this concept so far. All right, it doesn't, for malleable and ductile, it doesn't have to be a bowl and wire. It could also be other examples you can think of in your typical life. All right, there's lots of examples we can think of. So, all right, all right, so almost all positive. That's awesome. Let's move on then to a practice problem. So, so our whiteboard tools are on. So let's use our box tool. We're going to put a box around the correct option here to complete the statement. Remember, metals tend to have 1 to 3 valence electrons. So what do they prefer to do with these electrons? Do they prefer to gain or lose, or keep the same number? Great. I see Tara up there, Shane, Rosa, Luca, awesome. Evangelina. Yeah, so it seems like you guys are doing pretty well with this concept. So for number 3, be sure to put that answer that we were saying about this statement. That in general, the metals tend to lose those valence electrons to drop down to a full shell. All right, so for number 3, mark that answer on your notes. I'll set a timer.
So what I want to know is which of these following atoms is a metal? Remember, metals only have a few valence electrons. That means they have 1 to 3 outermost electrons. So we don't even need to know the actual elements here. Go ahead and on the whiteboard, circle that for me. Which of these only has 1 to 3 outermost or valence electrons? All right, perfect, perfect. Yeah, exactly. I see tons of answers up there. This is absolutely correct. If we take a look at this one right here, we can definitely see that if we ignore everything in the center, right, this one right here only has 1 valence electron. That is definitely going to make it a metal because if it has 1 valence electron, it's going to be, right, our two options are to gain 7 more to get to a full octet, or lose the one that it has. Tell me in the chat box which one is easier, to gain 7 more or lose the one that it has. Gain 7 more or lose the one that it has. Yeah, it's definitely much easier just to lose the one that it has, right? And anytime we lose electrons, that makes it a metal, right? So losing electrons, valence electrons, makes it a metal. So taking a look here, that's going to be the correct answer for number 4. This is actually sodium metal. It only has 1 valence electron that it prefers to lose. Please answer number 4 and then raise your hands, and then we'll also talk about why B and C are not metals. Raise your hands. Go, go, go. All right. So taking a look here, so B and C are not metals. The reason being is if you take a look at neon right here, neon actually has 8 valence electrons. And remember, our octet, right? Our octet says that things want 8 valence electrons. So if neon has all 8 of its valence electrons, is it going to want to bond with anyone else? Is it going to want to change its electrons? If it already has all 8 of its valence electrons, is it going to want to bond or change? No, so this is extremely stable. So this is actually a part of a group called the noble gases. If you think about the word noble, like nobility, you can think of it as like they don't like to mix with the commoners, right? So ancient nobility, they don't like to mix with peasants or with the commoners, right? So noble gases don't bond, they don't change their electrons at all, okay? Generally. There are some circumstances, but very rare circumstances. Now, phosphorus is also not a metal. It's called a nonmetal, and that is because it actually wants to gain electrons. So we saw at the start of class, Mr. Bangle was talking about that colored periodic table, and we saw in yellow that there are nonmetals. Nonmetals have 5 valence electrons, so they just need 3 more. Or sorry, they have 5, 6, or 7 valence electrons. So they just need a few more to fill their current octet. So phosphorus has 5, it just needs 3 more. It's going to be easier to gain a few more. That would mean it's definitely not a metal. It's actually a nonmetal. So let's go ahead and try number 5 on your own. I'm going to go ahead and clear these out. Raise your hands for number 5. Again, the question is very similar. Which of these is most likely a metal? Please do not put answers in the chat. Oh, sorry, Jasmine. I might not have seen your hand. I apologize. All right, so taking a look here, which of these is most likely a metal? Remember, metals only have a few valence electrons, 1 to 3 outermost electrons. So that's what you're looking for. You don't even need to know the identity of these. You just need to look at the outermost electrons. Raise your hands for number 5. You have 20 seconds. Go, go, go.
One more property about metals that we need to look at is something called conductivity. So we tend to say that metals are good conductors. And what we mean by that is that a conductor is something that can transfer energy very, very efficiently. So metals can do this 2 separate ways. One way is that they can transfer energy like through a wire with electricity, and the other is through a metal medium or surface, like with a pot or a kettle with heat energy. So as we can see right here, our electrical wires, they have a bundle of very, very tiny copper strands in the center that allow electricity to flow freely, kind of like the electrons are bouncing against each other like bowling pins, and they're transferring electrons from one end of the wire down to the other end. All right, this is important property because this is basically what allows us to use any electronic device that we are currently using today. All right, and one other part of the wire that's actually important but is not a metal is actually what we call the insulator. All right, that is what allows us to grab and replace or manipulate the wires without electrocuting ourselves. because insulators resist the transfer of energy. And then lastly, the transfer of heat energy with in terms of maybe like cooking food or boiling water, right? That's done with metals through a metal surface like a pot or a kettle that allows you to boil your water for tea or to boil water for maybe cooking like something like pasta. Yes, exactly, Tara. Yeah, electrical tape is another insulator that prevents you from getting electrocuted if you're like an electrician working on like house wires. So, all right, moving on from there. So in your notes for number 6, be sure to mark flow and thermal, those two words, flow and thermal for number 6. And then when we are done, ready to move on, be sure to raise your hand or send me a message in the chat box.
All right, so the last property we need to learn about is luster. So metals have metallic luster, or we can say they are lustrous, which means that they tend to be shiny. So you can see several pictures right here of different metals. All of these metals have different variations of shininess. Some metals definitely are more lustrous than others. The ones that tend to be the most lustrous are also the ones that we tend to use for jewelry, like for example, gold, silver, and platinum are all highly lustrous. They're very shiny. They also are pretty non-reactive with environments, which means that they can last for centuries. And so that is why we tend to use these things, gold, silver, and platinum, for jewelry. Now, taking a look here, you can also see an example of mercury over here, a picture of mercury, which, yes, looks kind of like slime. Mercury is also an extremely shiny metal. It's also, however, a unique metal because it's the only metal at room temperature, specifically 20 degrees Celsius or 68 degrees Fahrenheit, that is a liquid and not a solid. So every other metal on the periodic table at room temperature, meaning at 68 degrees Fahrenheit or 20 degrees Celsius, are all solids. There are a couple other metals that are close to being liquids at room temperature, like cesium or gallium. Gallium you can actually hold in your hand and it will melt in your hand because your hand is warmer than room temperature. But it actually needs to be at like 85-ish degrees to turn into a liquid, which is technically a little bit warmer than room temperature. So if we take a look at the definition of how we often define room temperature, the only one at room temperature that is a liquid is actually mercury. The other ones need to be a little bit warmer, from like 80 to 100 degrees Fahrenheit. Yeah, so that is a good point, Eva. Mercury is a toxic chemical. So how many of you have ever seen like the old school thermometers that have mercury in them? You might have heard about your parents opening them up when they were younger and playing with the mercury. Mercury is a ton of fun to play with. However, you really shouldn't touch it with your bare hands because it is toxic over time. You definitely should not ingest it. Yeah. So if you play with mercury, again, a short-term exposure probably won't hurt you, but you should use gloves when you play with mercury. It is a lot of fun to play with, though. It's really cool to see in your hands. And this is also something that is like dangerous because it builds up in a certain type of animal. So we don't eat a lot of what type of animals because they often have mercury buildup in them. Tell me in the chat. What kind of food do we often not eat a lot of? Yeah, so there are certain types of fish that have a lot of mercury that build up in their systems. So you don't want to eat too much of some of these fish just because that could cause mercury toxicity in your own body. Again, little amounts aren't going to hurt us, but over time they could build up. So yeah, so exactly. Do not consume the forbidden juice. It might look like lots of fun, but please don't drink this. All right, everyone. So let's go ahead and match these up for me up on the whiteboard. I'm going to give you your whiteboard tools. So what does malleable mean? What does ductile mean? What is a conductor? What is luster? And what is mercury? Go ahead and get your answers up on the whiteboard. Yeah, interestingly enough, you guys probably know at this point that like lead is dangerous and you shouldn't drink lead. But the ancient Greeks, for example, would actually synthesize a type of sweet syrup that they would make in lead pots because the lead actually made the sweet syrup even sweeter, and then they would drink it. And so a lot of them had lead poisoning. Yeah, because they wanted sweet food. Yeah, right. All right, looking good. Let's go ahead and take a look at our answers up here. So yes, malleability and ductility have to do with hammering and stretching into wires. However, we have these ones backwards. So the way that I like to remember this is malleability is a much wider or longer word. So malleability actually has more to do with the ability to hammer into sheets. Okay. Whereas ductility is actually the ability to stretch into a wire. The way I remember that again is ductility is a much thinner word, and so it's skinnier, and so you can think of it as being stretched into wire. Smiley faces or emojis in the chat box if that helps you better remember them. We often talk about them together anyway, so it's not a huge deal, but technically malleability is more about hammering into sheets, ductility is more about stretching into wires. I don't know, that's a good question, Creek. I would have to look that up. Yeah, yeah, definitely can lose the ability to reproduce. Yeah, exactly. Conductors, yes, conductors are the ability to carry energy. Two types of energy we talked about were thermal or heat energy, as well as electrical energy. Both of these have to do with the electrons in metals. Metals are unique in which their electrons can move very freely. And so that means that the electrons can move, which is what electricity is, that's moving electrons, as well as they can also move heat very easily. If you think about it like a game of telephone, they can send the heat message to one other electron very quickly, and so they can move it through a metal very quickly. Luster is how shiny something is, and mercury, again, is the only liquid at room temperature that is a metal. This is number 7. Go ahead and raise your hands when you have number 7 saved. You have 30 seconds to get that done, and let us know in the chat how you did. I already see tons of people telling me you got A's. Awesome, Jasmine, Eva, Matt, Haley, Alejandra. Great job, everyone. Ductility is the wire one, Shane. Malleability is the sheets one. Again, just think about malleability is much wider, kind of like a sheet. Ductility is much skinnier word, kind of like a wire. That's how I remember it.
All right, good job, everyone. So just to review, we just learned how to explain how atoms gain or lose electrons to have them able to obtain that full valence shell. We determined that metals do tend to lose their electrons, and we identify many of the main characteristics of metals. All right, so go ahead and use your pointers if you want. Tell us how you feel about this lesson. Should expect a lot of awesomes in this class. Yeah, I love seeing that. Good job, guys.